So, all right, what we're going to be talking about today is concavity. And so concavity is the way in which something curves. Okay? We can have two types of concavity. We can have something that is concave upward or concave downward. Okay? Put the candy away. Got to focus. Okay? All right. Pass it on back to Noah. Put it away, Noah.
It's simple. It's been sitting right here.
I know. All right. Okay. So, there are two ways that you can have something that's concave upward. It can be decreasing at a decreasing rate or increasing at an increasing rate. All right. So, on your paper, preferably in pencil, I want you to try to draw a graph that is decreasing at a decreasing rate.
Oh, okay.
So it's definitely got to be going down.
Oh, I know what you're saying.
It is not going to be going down in a straight line because that has no concavity.
I got it. Oh, it's an L. Like that.
All right. Okay, so Thomas, let me see what you drew. Okay, Thomas drew something that looks like this, sort of.
But it's an asymptote.
It should not have an asymptote.
Well, I never reached it.
Well, yeah, it can have an asymptote, horizontal asymptote. It's fine. Yeah. So it's definitely decreasing, and if we think about our rate of change, how quickly this is decreasing, our rate of change is our tangent, right? So, like here, our rate of change is pretty steep, but here, not so steep. Right here, not steep at all, right? So, this is decreasing at a decreasing rate. All right, draw me something that's increasing at an increasing rate. Okay. Noah has this. You guys agree? Okay. And so, at the... Thank you. So, like here, not very fast. Here we're increasing more quickly. Super steep over here, right? So, increasing at an increasing rate. All right. So, for both of these, all right, so in both of these cases, our derivative, our slope of our tangent line, what is happening to the value of our slope of our tangent line? For this one, okay, so what would we say it is here? Like, let's make an estimate. Maybe maybe that's a -5, right? That green line, what would we say? Maybe -1? Yes, slope. All right, the purple line, -1/2, right? Are those values increasing or decreasing? They're increasing, okay? So because they're negative. If they were positive, they would be. So f prime of x is increasing. Here, this would be like a +1/2. This would be a 1. This might be a 3. No, it should say I and C. Alright, so here, f prime of x is also increasing. Okay? So if the first derivative is increasing, then we know that the original function would be concave up. Let's talk about concave down. Increasing at a decreasing rate. Somebody show me what that would look like. No, it will going up, but not as fast at first, and then slow towards the end. Right? Square root functions look a little like that. Yeah. And natural logs too. Okay. All right. Decreasing at an increasing rate. Slow. We're dropping slow at first, then fast towards the end. So if we think about our slope here, if we think about those tangent lines, this might be a slope of maybe 2. This might be a slope of 1. This might be a slope of 1/2. What's happening? Don't say it. What is decreasing? The slope, or our f prime of x, is decreasing. Is that going to be the same here? Here we got these tangent lines. So this is negative 1/2. This might be like a negative 1. This might be like a negative 5. So those are also decreasing because we have negative values there. Okay, so, all right, so for concave upward, if a graph is concave upward, the slope of the tangent line increases from left to right. So the slope of the tangent line here, that is f prime of x. All right. So if f prime of x is increasing, then we know that f of x is concave upward. All right. The opposite is true for concave downward. If the graph is concave downward, the slope of the tangent line, which slope of the tangent line is the derivative, decreases from left to right. Or another way we could say that to condense it down, if f prime of x is decreasing, f of x is concave downward. Okay, so let's, all right, so I'm going to summarize this in a little bit different way too. So if I know f prime is increasing, so we have stated this part right here, right? We've already stated if f prime is increasing, then f of x is concave up. So if f prime is increasing, what do we know about its derivative? It would have to be positive, right? Because if we have a function is increasing, its derivative is positive. And again, we already have said this. If f prime is decreasing, f is concave downward. So, if f prime is decreasing, its derivative is going to be negative. So, you really don't have room. I don't know where the best place to put this would be. Actually, I do know. I copied the last page of this and shouldn't have, because the only thing on your last page is just the assignment. So, there's plenty of room for you to put this there. I'm just going to put a new page right here. So I like to think of this, I like to make myself a chart for this to think about what information it gives me. So I'm going to do x. No, I don't need x on this. I need f of x, f prime of x, and f double prime of x. And we're going to have, let's see, 1, 2, 3, 4. All right, so what we've done up until this point is we said that if my first derivative was positive, it told me that the function that it came from was increasing. And if the first derivative was negative, what did that tell me about the original function? Decreasing. So that's what we've been learning so far, right? That's before we got here. So what we're talking about today is we're saying if f prime is increasing, that tells me that f of x is concave up. And if f prime of x is decreasing, f of x is concave down. Not f prime. But, so if f prime is positive, all that tells us is that our function is increasing. So it does not confirm concavity at all. So knowing whether your derivative is positive or negative does not tell you concavity. But if my derivative is increasing, so if a function is increasing, what do we know about its derivative? It's positive. So the derivative of f prime is f double prime, so it must be positive. Yeah, and so if we know that f prime is decreasing, then we know that f double prime would have to be negative. So what we actually find ourselves doing is most of the time to tell about concavity, especially if it's not a graph, if it's an equation, we look at the second derivative, because if my second derivative is positive, my function is going to be concave up. If my second derivative is negative, my function is going to be concave down. Say that again. Unless they give you a graph, yes. No? Not right now. We need to stay here. All right. Okay, so let's go back to this problem. Here. All right, so we're supposed to tell the intervals where f of x equals x to the third minus 9x squared plus 24x minus 12 is concave up and concave down. So if I can find the second derivative and tell whether it's positive or negative, that will tell me whether f is concave up or concave down. So, correct. So this one is pretty straightforward for finding your derivative. You got 3x squared minus 18x plus 24. And then do it again. So 6x minus 18. Okay, so we're going to do basically the same thing that we do whenever we're doing the increasing, decreasing, maximum, minimum stuff. We're going to take our second derivative and set it equal to 0. So 6x will equal 18. So x will equal 3. Now, I don't know why nobody has came up with a name for this point right here. It is not called a critical point. Critical points are only for the first derivative. There is no name for this that's like standard and agreed upon for mathematicians. So we should probably come up with a name for it that we want to use, but we're not going to put on the AP exam.
A double crit is a Hyatt number. Super point. A double crit is super crit.
What do you think, Thomas? Huh? Steve? Let's not do Steve. What do you think? What? The cliqual point. I like that. Kind of like that. let's call it, I like the double critical.
Just call it the super point.
But, so, I had not come up with that ahead of time, but if you would rather call it Steve or the Kachow point or whatever point you want to call it, just don't write it on the AP exam because there's no agreed upon name on this. So if you call it the Steve point, they're not going to know what in the world you're doing. Just don't call it anything on the AP exam, okay? You don't have to call it anything, but it's like a critical point, but it's for the second derivative, so it's not a critical point. But we're going to do the same thing we did. We're just going to make ourselves a sign line. We're going to put 3. We're going to think about the second derivative. So if I plug in a number below 3, like 0, I'll get negative. If I plug in a number above 3, I'll get a positive.
And wait, are you plugging this into absolute?
Plug it into the second derivative. Second derivative. Yeah. And so this is my second derivative. So, let me move this down a little bit. So if this is my second derivative, then it tells me the f prime is decreasing here and increasing here, I know. And then it tells me f of x is concave down here and concave up here.
So, from negative infinity to 3 is concave down. Is it always going to be that straightforward? Probably not.
The equation gets more difficult, but the idea is the same.
So, like,
Yeah, the equation may be more difficult. We're taking that second derivative
the derivative
would be more complicated.
realizing if it's concave up or down.
But concave up or down is just always,
Just that straight.
and you don't, this line that I put right here, you could leave it out right there. So you can just talk about that second derivative. So,
Go straight to the normal. So
Yeah.
if it's positive, it's always going to be concave.
yeah, so whenever you're saying that, though, remember we cannot say it when we justify anything. So we would say, we can't say it is concave up. What is concave up? F of x is concave up for negative infinity to 3 because you talk about that second derivative. F double prime of x is less than 0, or the second derivative is negative there. So concavity, we generally want to explain that with our second derivative in most cases. And then we would say f of x is concave down. I said this backwards, didn't I? That should say down right there. Right? From negative infinity to 3, it's down. Concave up for 3 to infinity because the second derivative is positive. Okay, it's a lot like finding maximums and minimums, increasing and decreasing, but we're working with that second derivative instead of the first derivative. All right, and so a piece of terminology that you need to know here that you will definitely see on the AP exam is a point of inflection. Points of inflection are points where the concavity of the graph changes. Yes, there is one on the FRQ that you did not know how to do until now. Yeah. So now you should be able to do that part now. So at 3 right here, we would have a point of inflection. The question didn't ask us about points of inflection, but we would have a point of inflection there because our concavity changes. Your double critical points or your Steve points or your whatever points you want to call them, they are not necessarily points of inflections, but they might be. They're your candidates for points of inflection. Yeah, they're your nominees for points of inflection. Yeah. Okay. It's a point of inflection. So what happens there for this one? You're going from concave down to concave up. So that looks like this. Concave down, concave up. Or I guess it could look like this. Concave down, concave up. All right, I'm not sure if this function is increasing or decreasing. We'd have to look at the first derivative to be able to tell that, to tell which one of these it would be. That's your derivative, though, not your original function. So you would have to do like a sign line for the first derivative to tell whether or not the function's increasing or decreasing. Which we're not putting all of that together yet, so we don't have to worry about that. All right, let's see. Okay. All right, f prime of x here. We're going to use the chain rule for this. So we will have negative 6 x squared plus 3 to the negative 2 times the derivative of the inside, which is 2x. So that'll be negative 12x times x squared plus 3 to the negative 2. We don't do product rule in this step, but for concavity, we got to look at the second derivative. So we got to take the derivative again, and to find the second derivative, you are going to have to use product rule and chain rule. Yeah. So for product rule, you're looking at these two pieces are being multiplied together. So we would have here. Ethan, help me with this. What would we do to do the product rule for this one?
Negative 12x, and then since you need the chain rule for the next one,
okay.
You need a negative 2 out front, and then you need the parentheses x squared plus 3, and then you got to take the derivative inside, which is 2x, 2x, and then you since product rule, you plus,
okay.
And then you do the derivative of negative 12x, which is just negative 12 plus negative 12, and then you take the regular function x squared plus 3 raised to negative 12.
All right, you missed one little thing. It was right here. When you do your chain rule here, you do negative 2 x squared plus 3
yeah.
to the negative 3 power. So you just got to be careful not to miss that. But otherwise, good job. All right, so this is kind of a mess, though, right? Like, finding critical points is going to not be so easy for this. So let's clean it up. So let's do, we'll have 2 times 2 times, we'll have 48 x squared times x squared plus 3 to negative 3. That's just putting together this negative 12x, this negative 2, and this 2x. And then we'll just have minus 12x plus x squared plus 3 to the negative 2. Since these two right here match, we're going to factor out x squared plus 3 to the negative 3. We also, if we want to, could take a 12. Let's take that 12 also. All right, so 48 divided by 12 is going to give us 4x squared. And then we're factoring out that whole x squared plus 3 to negative 3, so it's just gone. All right. Minus 12, we're taking the 12 out, so it's going to be out front. We don't have to worry about it. Whenever we factor out that x squared plus 3 to the negative 3, what are we going to get over here? X squared plus 3. Make sure you distribute that negative. Oh, yes, thank you. And I would probably go ahead and send this back down to the denominator. So you got 12 times 3x squared minus 3 over x squared plus 3 to the third. You could take out a 3 if you want. So if you want to, you can make this 36 x squared minus 1 over x squared plus 3 to the third. You don't have to do that because you can still solve it just as easily without pulling it out. But you could take it out if you want. In fact, you didn't even have to take out that 12 that I took out. You could have left the 48 and the 12 where they were at and still been fine. Alright. So, that's a pretty extensive second derivative. One thing I would suggest for you as you do your homework on ones that are longer, maybe take the derivative in your calculator to make sure that you're doing it right. Don't do it all in your calculator, but you can do that to make sure that you're doing it correctly. So that, because if you get the wrong first derivative, you can't get the right second derivative. And if you get the wrong second derivative, you're not going to get the right answer. So that might help. So whenever we find this derivative, what do we do now? Top and bottom equal to 0. Is that bottom ever going to equal 0? X squared plus 3?
You just get rid of both sides. And then you subtract it down.
Yeah, so if you cube root, you'll get x squared plus 3 equals 0. You'll get x squared equals negative 3. And then you find yourself trying to take the square root of a negative. So you don't get in critical parts from that section. Over here, if you divide by 36, you got x squared minus 1 equals 0. So x squared equals 1. So x equals plus or minus 1. So those are our double critical points. Yeah, and so for this, you can use the chart if you want here, or you could just plug in. It doesn't matter. So if we use the chart, we're going to have -1 and +1 are our points. We got 36. We got x squared minus 1, and then we've got x squared plus 3 to the third. It is okay to leave off 36, but it's because all of it's positive, which is not going to change the sign. If that had been a negative 36, you would have to include it. So you could get away with not including it. The denominator, really, you don't have to include either, because when you take a number and square it and then add 3, it's still positive also. So really, it just comes down to x squared minus 1 is what's going to determine our sign here. So if I plug in something like negative 2, I'm going to get a positive. If I plug in 0, I'll get a negative. And if I plug in something bigger than 1, like 2, I'll get a positive here. So that gives us a second derivative that's positive, negative, positive. So we're looking at that second derivative. Its sign is what's telling us our answer. So where we, so I would say f of x is concave up for which sections? Negative infinity to negative 1 and 1 to infinity, because f double prime greater than 0. Yeah. Or you could say it's positive or whatever. And then we'll say f of x is concave down for negative 1 to 1, because f double prime of x is less than 0. So the concept here is exactly what we did on the last problem, but the work is more extensive because it's a more difficult derivative to take. Yes, it definitely means more room for error. Because we're cutting it close to the end of the class, and I know taking a second derivative of this with the quotient rule twice is going to take us a little while, we're going to skip it for right now and do a trig one. Because everybody loves a little trig. But the derivatives are easy for trig. Especially trig like this, right? This trig should be pretty easy. Alright? Okay, very good. Alright, so I like it whenever the derivatives don't take up a lot of my time here. So we want to know where that second derivative equals 0. So basically, we're just asking ourselves, when does sine x equal cosine x? And there's 5 of you that probably know, and 10 others that it's questionable whether or not you know. Alright, so it's right here. Here you got root 2 over 2. Root 2 over 2. You guys know the coordinates a lot better than you know the radian measures. That's pi over 4. Right there. I don't have time to do that right now, but at the beginning of the class, let's try to do it. I'll show you the way that I think about it. Okay? Yeah. So it's this, and this is 5 pi over 4. So we got x equals pi over 4, and x equals 5 pi over 4. So we're going to make ourselves a line here, and we're going to look from 0 to 2 pi, and then we're going to put pi over 4 and 5 pi over 4. So, this first section right here, the only value we know between 0 and pi over 4 is pi over 6. And at pi over 6, square root of 3 over 2, 1/2. We're plugging it into the second derivative, so it's negative cosine of pi over 6 plus sine of pi over 6. Cosine is root 3 over 2, so negative root 3 over 2 plus 1/2. It doesn't matter what the value is it positive or negative? It'd be negative because the root 3 over 2 is larger than the 1/2, so I have a negative here. Alright, next section, pi over 4 to 5 pi over 4. Pi is probably your easiest thing to plug in here. So we're doing negative cosine of pi plus sine of pi. So coordinates here, negative 1, 0. So you got negative, negative 1 plus 0. That's going to give you a positive. Then we're here. 3 pi over 2. Probably our easiest one here. Here our coordinates are 0, negative 1. So we got negative cosine of 3 pi over 2 plus sine of 3 pi over 2. So like I said, negative 0 plus negative 1. And that is going to give us a negative right there. So you can see this unit circle stuff creeping in a little bit more. Well, I need you to know it really well. So this asks for concave up. So where would our graph be concave up? 5 pi over 4. So f of x is concave up for pi over 4 to 5 pi over 4 because the second derivative is greater than 0. Okay. Yep. Yeah. Yeah, we don't have to do concave down on this because it only asks for concave up. All right. Okay. All right. Points of inflection. A point of inflection is where we switch concavity. So there's not a lot of difference here than other. Right, those would be your x coordinates. If it needed your y coordinates, you'd plug back into the original to find the y coordinates. Most of the time, those problems just ask for the x coordinates. So yeah, 5 pi over 4 and pi over 4 would be our points of inflection there. So if we want points of inflection, we got to find second derivative. I'm going to write this first as natural log of x squared plus 4 to the 1/2. Now, there's a property of logs that can make our life a little bit easier here. What can I do with this exponent right here? I can write it out here out front. So I can write this as 1/2 natural log of x squared plus 4. And that's going to make it easier because we don't have to do like a triple chain rule. Now it's just a regular chain rule to do that. It's just a property of logs that we learned in pre-calculus is always true. So if you have an exponent like that, you can pull it out front. Yeah, I'm sure there's a proof for it somewhere, but right now just take my word for it.
Kind of just trust the process.
All right, so f prime of x. The 1/2 is going to stay out front. It's just a coefficient. What's the derivative of natural log? 1 over x, or in this case, 1 over x squared plus 4. But I've got to use chain rule, so I've got to multiply by 2x. So if that 2x is like a 2x over 1, so I end up with 2x over 2 times x squared plus 4. But the 2's can cancel, so just x over x squared plus 4. So no natural log anymore, that's good. Now I got to take a second derivative. Quotient rule this time. Selena, tell me what to do for that second derivative. We don't take the derivative here, so x squared plus 4. 2x is different than x squared. X squared plus 4. Okay, times 1 minus. There we go. All over. Good. Good. Alright, so we got x squared plus 4 minus 2x squared over x squared plus 4 squared, which is going to give me 4 minus x squared over x squared plus 4 squared. We okay here? We've got to be because we don't have much time left. Okay. Alright, so the numerator, 4 minus x squared equals 0, so that's 4 equals x squared. We will square root both sides. We'll get x equals plus or minus 2. On the bottom, we square root both sides. We get x squared plus 4 equals 0. That's x squared equals negative 4. I got to square root both sides. Can I take the square root of a negative? No, not without an I, so I'm not going to get any super critical points there. Double critical points, whatever we want to call them. Just because of the nature of the numbers, like if you square a number, it's going to be positive, no matter what number it is, even if it was a negative number to begin with. And then if you add 4 to it, it's going to become still more positive, right? And then you're going to square it again, which makes it positive, right? So that has to always be positive, so it can never equal 0. So sometimes it just happens that that's the case. All right, so second derivative. Negative 2, positive 2 are our numbers. And we have got, we already said the denominator is always positive, right? So you could leave it off, or if you do include it, x squared plus 4 squared, positive all the way across. 4 minus x squared, if we plug in something like a negative 3, we'll get 4 minus 9, that'll be negative. If we plug in a 0, we'll get a positive in the middle. If we plug in something like a positive 3, we'd get another negative. So we end up with negative, positive, negative here. Alright, so points of inflection, and I should say I only want x coordinates. We're only going to do x coordinates for sake of time anyway, right here. So we would say, this is what, so your reasoning for points of inflection is a little bit different than concave up or down. No, points of inflection is when you're going to go from negative to positive or positive to negative. So you got to change signs. Yeah. So we would say f of x has points of inflection at x equals negative 2 and x equals 2 because we'll say f double prime of x changes signs or sign. Okay. It's a lot like maximums and minimums. At maximums or minimums, we have to talk about the derivative changing positive to negative or negative to positive. For points of inflection, the nice thing about it is it doesn't matter if it went negative positive or positive negative. There's still points of inflection. So there's not a special name for each one. All right. So we did not get to the E, but it's the same idea. Here is your assignment that you're going to do for me. Some of these first ones should be really straightforward. A few of the last ones might be a little bit tougher. On those second derivatives. If you're getting stuck, maybe use the calculator. I want you to be able to do them by hand, but use the calculator if you're getting stuck on a derivative.